All right, thank you for coming. I'm presenting joint work with my co-authors Tongpeng Liu and my advisor Emery Berger on Dthreads. So in the beginning, we had the core, and the core was good. It gave us our daily speed. Every 18 months, our programs ran twice as fast, and we didn't have to do anything until the apocalypse. And we were stuck. And then came a false prophet, and now we get multi-core, which is maybe not so great. So now we have multi-core, and we can run our programs faster just like we did before. But if we want speed, we just need to use parallelism. So that's not so hard, right? We just use threads. So you all see this as a correct program, right? Now, it turns out it's not quite so simple. When you run parallel programs and you just convert programs to use pthreads, you get race conditions, and you see different output on every run. And sometimes it works just fine to keep you guessing. In fact, most of the time it keeps you guessing. And then you ship your product, and there's a bug. So again, not so great. So with pthreads, we run into these four major problems. We have race conditions, we have atomicity violations, deadlock, and order violations. But maybe there's salvation. There's this product called GNU Portable Threads. It takes your processor, and it uses cooperative multithreading, and it resolves all these problems. There's just one issue. It turns out it's kind of slow. Now I'm presenting Dthreads, and what Dthreads does is it takes pthreads, and it sets your race conditions, your atomicity violations, deadlock, and order violations in stone, and makes them deterministic. So we've removed the daemons from your parallel programs. Now Dthreads enables a few things. One of them is a race-free execution. A race occurs when you have a non-deterministic output. If you always produce the same output, there's no race. It allows you to do replay debugging without any need to log every memory access. You just checkpoint, roll back, and replay the inputs to the program. And it allows you to do efficient replicated state machines without any need to communicate between servers. Now, Dthreads is efficient, and I'm going to take a look at these results here. So in most cases, it's faster than the previous state-of-the-art system. You can see here it's dramatically faster in nearly all of these cases. It's generally as fast or faster than pthreads, and I'm going to come back to these cases a little bit later. So Dthreads is easy to use. All you do is you take your program that you're building with pthreads, and you flip over your P. There's no kernel support. You don't have to change your source code. You just relink the program. This could just as easily be a .o file. Now Dthreads does a few things. One of them is it runs your programs with threads in isolation. So in a conventional parallel program, threads run in a shared address space. But with Dthreads, we take your threads and we turn them into processes. And that means that you run in disjoint address spaces. Now you might be thinking, we use threads because they're fast, right? Turns out that's not the case. So here what we've done is we've taken a program that spawns off parallel workers, either as threads or processes, and they perform work for either 1, 2, 4, up to 1,024 milliseconds. And now we normalize the execution time of these programs to the pthreads implementation. So for large workloads, pthreads and processes perform essentially the same. But for small workloads, processes actually run faster. This is somewhat counterintuitive. It turns out it's a quirk in the Linux scheduler. It seems to appear in other operating systems too, but we've specifically targeted Linux. So if you imagine you have your multi-core again, and you have these 4 cores running with 1 thread on one of the cores. Now, on Linux, when it spawns more threads, those threads live on the same core. And for some time, they'll stay there until the scheduler decides that these are not short-lived threads and migrates them to other cores. And it does that because you don't pay a cache penalty when threads live on the same core, but you don't get the parallelism of running them actually concurrently. Now, with processes, the instant you spawn a new process, it distributes it to other cores. There's no shared cache. There's no benefit to keeping it on the same core. It would only introduce overhead. So with separate processes, we immediately get the parallelism that you need for efficient programs and scalable programs. Of course, there's an issue. When you run threads as processes, they no longer have shared memory, and we need to preserve those semantics. So what we do is before a page is modified by your program, we take a snapshot of global state. And we find the difference between the program's global state after modification from the snapshot, and we just write back the changes. And we do this at a page level, so only modified pages need to be snapshotted. Now, we have isolation, but if we want determinism, that's not enough. We need to expose updates at deterministic times while the program is running, and in a deterministic order. So your program runs in a parallel phase until it reaches synchronization operations. Now, these could be lock acquisitions. They can be condition variables. They could be thread creations. It also includes file operations, since threads can communicate implicitly through files. At the end of the parallel phase, all threads have reached some synchronization operation, and this is when we take our snapshot. Now, the first thread begins with a token. We use this token passing protocol, so threads take turns in a particular order, and it commits its updates and runs the critical section of the lock it may have acquired, passes the token, and the next thread does the same, and so on. And then we return to the parallel phase, and the execution continues. Now, going back to the performance numbers. So there are several cases here where Dthreads does not perform particularly well. So in 3 of them, it seems to be that the rate of acquisition of locks or synchronization operations leads to high overhead in the commit protocol. So more synchronization operations means more commits, which means more time spent not running parallel code. These same programs also have a load imbalance problem where some threads need to wait for a straggler. And then in one case, the number of pages touched by the benchmark leads to a large overhead in commit because it modifies just a few words on a large number of pages. And it's worth noting that this is an unusual benchmark. It has a strange workload. It actually randomly picks addresses and modifies them. And this is, in very many ways, a worst case for Dthreads. Now, here's some cases where Dthreads actually outperforms pthreads. This is a little surprising. It's not a result we're going to complain about, but we want to know why. And it turns out the culprit is false sharing. Now, just to refresh your memory, false sharing occurs when you have 2 threads running on separate cores, accessing distinct variables that happen to fall on the same cache line. Now, when the thread running on core 1 modifies a word in its cache line, this leads to an invalidation in core 2, and a write back and a read out again for core 2. Now, core 2 modifies a word, not the same word as before, and again, we have an invalidation. The performance can degrade by as much as 20x. That's the penalty for going out to memory versus going to the lowest level of the cache. And this dramatically hurts scalability. So now with Dthreads, we're not using threads anymore. We're using processes. And this actually resolves false sharing. Now, when you run a thread as a process, you have a distinct virtual address space. And so when core 1 reads its cache line and core 2 reads its cache line, they're not the same cache line. They're separate virtual address spaces. They can't share data directly through the cache. So they can proceed with their writes, and they don't lead to any invalidations. So here I'm going to take a look at some components of Dthreads. So Dthreads has 2 major pieces. It has the ordering of synchronization operations and commits, and then it has the isolation mechanism. And now you can see that in most cases, the overhead from Dthreads comes from the isolation mechanism. And in 3 of these cases, the overhead is precisely due to the synchronization operations putting load on the commit protocol. These are the same ones that ran slowly before. And then these are the cases where we observed false sharing, and you can see that for 2 of them, isolation actually buys you a performance gain, whereas string match, this benchmark here, where they're all the same, ordering is what gives you some of the performance boost, largely due to some optimizations that we've implemented to lower the overhead of doing Dthreads is also scalable. So what we've done here is we ran our programs on an 8-core machine, first with 6 of the cores disabled, and then we ran them again with all 8 cores enabled. And we compared their time. So an ideal speed up of this program would be 4x, so higher is better in this case. So there are a few cases where Dthreads doesn't scale as well as pthreads. This is probably due to load imbalance problems, potentially the commit protocol, but it's not a huge difference. There are several cases where Dthreads actually scales better than pthreads. Again, this is due to the fact that Dthreads solves false sharing problems. So in conclusion, Dthreads takes your atomicity violations, your race conditions, deadlock, and order violations, and sets them in stone, giving you a deterministic execution. It takes your program with threads and turns it into a program with processes. It's efficient, and it's easy to use. Thank you for your attention.
Question?
Hello, Yu Fei-Chen from Fudan University. So my first question is that different processes wait on the fence until they call some synchronization operation. So how do you know that how many processes wait on a specific, say, lock? And then you know when the fence or all the threads come to the fence.
So it's not, it doesn't have to be the same lock. Is that the question you're asking?
No,
Okay.
let me give, for example, if the different processes are waiting for the same lock, so how do you know that how many threads are waiting for the, we are going to acquire the lock?
So we know how many threads there are. We've intercepted every thread creation call.
If there's only, say we have 3 threads, but actually there are only 2 threads which will acquire the lock.
So we have to wait for that third thread to reach some synchronization operation. So that's where the load imbalance comes from.
So is it possible to have some deadlocks if there's, say, a single lock, but there's only one thread acquiring the lock?
So when a thread actually exits, that also counts as a commit point. So as long as your threads don't run on forever without ever doing any synchronization operations, we don't believe it will lead to deadlock.
Thank you.
Safa Melander, Bell Labs. I'm puzzled by this because suppose that you know something about the execution of the threads and you know that you don't need a lock in some particular case, but you still have sharing.
Right.
How do you discover the sharing in the first place?
Right. Well, so one of the issues with Dthreads is that we don't support ad hoc synchronization. And that includes anything that depends on racy behavior. So if you have a racy counter and you update it, those counters will be updated in isolation and updates will clobber each other when they commit. So it's a limitation of the work, although there's some work last year in OSDI showing that ad hoc synchronization and racy behavior can lead to buggy implementations.
Okay, so how do you know what a lock protects? Because
we don't. So every modification made while holding a lock or not holding a lock is done in isolation.
I see.
So we guarantee atomicity, not necessarily that updates will merge in the way the programmer expected. But we do preserve the semantics of pthreads.
You preserve some semantics somewhere. Yeah.
We leverage the undefined behavior in pthreads.
Okay.
Thank you.
Christian Zanthiri, PFL. Since a lot of these are scientific benchmarks, and a lot of them also had considerable false sharing, I was wondering exactly what is the overhead on other types of applications where, for instance, false sharing does not make Dthreads look better.
Well, so the first thing I would point out is that false sharing is not exclusive to benchmark programs or toy programs. It's very hard to find. There's actually some work done by one of my co-authors appearing at Uppsala yesterday that addresses some of this. So, I mean, Dthreads is helped by these false sharing problems going away. And I believe I have a slide showing you. Well, I won't do that. Okay. So here I have the overhead again of Dthreads, excluding the outliers, which I've highlighted. And you can see without outliers, it's marginally slower than pthreads. But in the common case, Dthreads is very close to pthreads.
Okay,
So,
thanks.
Hi, John Osterhout from Stanford. I'm curious about the memory model. So
you make copies of the memory for each of the separate processes, but how do modifications get reflected back to the other processes again? For example, suppose one of the threads writes every odd word in a page, and one other thread writes all the even words in a page.
Right.
During the part where they're running in parallel, how do you merge those back together again to other threads that might need to look at a combination of that information?
Right, so when your thread goes to commit, we take a difference between the thread's view of the world and the previous global state, and we just commit the changes. So in your example, the odd modified words would be committed back by the first thread, and only the even modified words would be committed back by the second thread.
And how does this scale? Would this work well in a process with, say, gigabytes of address space? I assume these are relatively small benchmarks here.
So the working set has a big effect, but it's the working set in each transaction, so between synchronization operations. So if your program touches a huge number of pages between lock acquisitions, the overhead will be high. But with a large memory space, as long as your transactions are small or they have locality, which I think is a reasonably safe assumption in many cases, the performance is not bad.
Jean-Philippe Martin with Microsoft Research. It may be in the paper, I haven't read it. I was just wondering if you did anything special for like atomic compare and swap type of operations.
Right, so this C-anneal benchmark here, the one with the random working set, also uses lock-free algorithms. That could potentially be a source of some of the overhead. So the issue is that when you run those operations in isolation, you don't get the kind of communication you were hoping for. So we don't support that kind of ad hoc synchronization. Although it doesn't break the program, it comes at a performance cost.
Thank you. Jing Chen from Fudan University. I want to ask which version of Phoenix do you use in the benchmark?
I believe we use Phoenix 1. I think it includes all the benchmarks from later versions plus some extras.
Another question is, if all threads must acquire lock and begin synchronization before they enter the synchronization execution, if some thread may acquire the lock very, very long time later, so the first acquired lock thread will be wait a long time.
That's right. So this is the starvation problem we saw in these 3 benchmarks on the right here. So when one thread doesn't acquire a lock for a long time, you do potentially delay the execution of other threads.
So if there are no match for sharing in the benchmark, your result or the data will be worse than the pthread?
Yes, but just by 5%, which is considerably faster than the previous state of the art, where it's more like 2 to 4x in most cases and sometimes worse.
Okay, thank you.
Thank you.
Okay, let's thank the other.